Warning: the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This lecture begins a series on how to use calculus to really get an accurate graph of a function. And this leads into actually using calculus to optimize functions in the long run. So this is a multi-section topic. It takes us quite a while to develop all the skills we need. And so I like to let students know from the get-go that our ultimate goal here is to develop a process to accurately graph a function. So as we're going through this material, I will continually be creating a concise battle plan for graphing using calculus. So every step of the way, I try to remind you of kind of the tactics we're using. I'm not a huge fan of creating recipes like how-tos, how to do a step-by-step on how to do something, because really calculus should be more of a heuristic feeling, like a natural feeling for you rather than a memorized process. But when it comes to graphing, it is nice to have a list of steps. So we'll start this discussion by talking about the calculus of increasing and decreasing functions. And this is actually a gentle introduction to that topic. So let's take a moment to discuss the relationship between the derivative of a function and the increasing or decreasing behavior of its graph. Here we have a wonderfully fun looking function. It doesn't really matter what the function is, but you can see it's very jagged. It's got a lot of wiggliness to it, right? And so we're going to take a few moments here to talk about the derivatives and what that implies for the behavior of this graph. Now, this graph does not represent all functions. There are always, I shouldn't say always, but there are exceptions to some certain statements. However, let's go ahead and just take a look at, let's say, this interval from what seems to be negative 2.5 to negative 1.5. So the interval right here from negative 2.5 all the way down to negative 1.5. In fact, negative 1.515 up to negative 2.535. You can see that the function's definitely decreasing. That's an algebra skill, just to say that that function is decreasing there. And really what I want to draw your attention to is the idea that the derivative of the function is negative. Now that should be very obvious and something that we've probably talked about already. However, this is a theorem in this section or in this video, is that as long as our derivative is negative, we know our function must be decreasing. And likewise, if our derivative is positive on an interval, we know our function is increasing. And in fact, I could really quickly showcase what the derivative of this function looks like. And now that I said that, it looks pretty terrible. So I'm going to go ahead and just try to zoom into a small little piece here. So let's take a look at, again, from negative 537 or something like that, all the way to x equals negative 1.515, or yeah, something like that. Notice the function is in red, and the blue function is the derivative. And notice that the blue function goes negative here. It's below the x-axis from x equals negative 2.537, which is basically where this right here starts to dipping down. And the blue curve remains below the x-axis, in fact, significantly below the x-axis, from that negative 2.537 all the way up to negative 1.515. So the blue curve is below the x-axis, the blue curve being the derivative. So the derivative is negative here. And notice at the very same time, on that very same interval, the red function, which is the base function, was decreasing. So that's a good justification, not a proof, but a good justification that as long as a function's derivative is negative, that function must be decreasing. And if the function's derivative is positive, the function must be increasing. And this leads us naturally to this theorem. The increasing-decreasing test is what we're going to call this. By the way, some people use this notation, the ID test. I usually don't actually write out the names of these tests. I don't even recall the last time I ever wrote down the names of these tests that we're going to be seeing throughout these series of videos. Because I just don't like to name things unless it's like the Pythagorean theorem or maybe the quadratic formula or the intermediate value theorem or something like that. But when you start getting the tests like this, I tend to not state them. So sometimes I just naturally say, well, the derivative is positive, so therefore we know our function's increasing. So if I do not state the name of the test in these videos like this, then please forgive me. It's just a habit I have. So here's the increasing-decreasing test. If f prime is greater than 0 for all x in an interval, then f is increasing on that interval. Likewise, if the derivative is negative for all x in an interval, then f is decreasing on that interval. That should naturally make sense to us at this point in calculus. Let's go ahead and prove this. And the way I'm going to prove this is I'm just going to grab a couple x values from our interval I here. And specifically, I'm just going to assume that x sub 1 is just less than x sub 2. I just want some order in this proof. Also, I'd like to include some notation that you should get used to. If you have a couple elements in an interval, you can just separate them with commas, right? X sub 1, comma, x sub 2 are elements of the interval I. That's just notation you should probably get used to as we move forward in mathematics. Now, the proof I'm going to do here is going to be just for part A, because part B is a similar proof. And again, you'll just like with most of my videos, you'll have to forgive my terrible internet. I live in a rural area, so I do not have great internet. And for some reason, that affects the quality of my screen. And again, I just want to remind you, we're doing this proof for part A only. So since f prime of x is greater than 0 in part A, we know that f is differentiable, right? Because they told us the derivative is positive. So we know it's differentiable from x1 to x2. Now, I also want to mention here that x1 and x2, I'm going to assume are not the edges of the interval I. That is just for a very specific reason that I'm about to mention, but I'm going to assume that x sub 1 and x sub 2 are not the endpoints of I. In fact, let me write that cleanly right here. There we go. So assuming x1 and x2 are not endpoints of I, well, we know that f is differentiable on the entire interval I, because that's what our assumption is, if f prime is greater than 0 for all x in an interval I. So we know f is differentiable for every value on the interval I. Well, if I don't grab points from the end of the interval of I, then I know f is continuous on any interval contained within I. Okay, maybe I'm not saying that clearly enough, so maybe I should say this. Here's the interval I right here. Let's just say this is the interval I. All right, and we are going to grab, we know that f is differentiable on this entire interval, which means, by the way, it's continuous within that interval. I really have to change that highlighter color because that is not a highlighter, that's pen. But that just means that it's continuous on the interior of that interval, not at the edges, but in the interior of that interval. Differentiability implies continuity. And so we have continuity on the interior of that interval, and we're allowing ourselves to grab an x1 and an x2 within the interior of that interval. So therefore, not only is f differentiable between x1 and x2, but it's actually continuous on the closed interval from x1 to x2 because they're within the interval I. So that's just kind of important to note there. And I'm going to write that here. So there you go. The endpoints don't really matter for our interval here because you're never really going to have increasing or decreasing behavior at an endpoint. That's an often misunderstood piece of mathematics, and in fact some instructors or professors will actually disagree with this, but you can only have a function, an interval of increase or an interval of decrease, be open. You do not want to include endpoints on intervals of increase or intervals of decrease, because if you did, you're basically saying, so let's say that we have a function that's increasing from a to b. If you were to say, okay, therefore it's increasing on this interval, well, that means that at that little dot right there, you're saying that it's increasing at that exact moment, but that at a point it's not increasing. Over an interval it increases. So including the edges is really a bad idea. Moreover, if you did allow yourself to include edges, let's just pretend for a moment you allow yourself to include edges, then you're saying this function is increasing from a to b, including the edges a and b, and it's decreasing from b to infinity, let's just say, including b. Well, then you're saying it's increasing and decreasing at b, which makes no sense in this situation. So including edges for intervals of increase or decrease, bad idea. I've seen a lot of mathematicians actually include those edges. That's a bad idea, bad habit, bad mathematician. Anyhow, we have two very important conditions that we have going on here. We have continuity on a closed interval and differentiability on the open interval, which allows us to use the mean value theorem. And when I introduced the mean value theorem a few videos ago, I mentioned that it's used quite a bit in proofs and in theory, and here we have it again. Well, by the mean value theorem, there exists some number between x1 and x2 such that f prime, or the slope of the tangent line at that point, is equivalent to the slope of the secant line connecting x2 comma f of x2 to x1 comma f of x1. So there you go, we have that. Now I'm going to go ahead and write this in its alternative form, which I tend to often have to do, but I never start with, just because I don't really memorize the mean value theorem in two forms. I just memorize it in one. So we get to this point right here. That's the alternate form of the mean value theorem. However, we were told that f prime is always positive, right? That was our assumption. There we go. It's all the way at the top here. F prime is always positive. So this f prime is a positive number. Also, we assumed x2 was greater than x1. So x2 minus x1 is positive. So let me just make that mention here. The left-hand side, whoops, maybe I should say there we go. The left side of the equation, of this equation technically, is positive. Therefore, the right-hand side of that equation must be positive. So thus, f of x sub 2 minus f of x sub 1 must be positive as well. That is, f of x sub 2 must be strictly greater than f of x sub 1, which tells us that f has increased between x sub 1 and x sub 2. So this implies f is increasing. The reason why I can say f is always increasing over that entire interval is because x sub 1 and x sub 2 were arbitrarily selected points. They could represent any 2 points where x sub 1 is less than x sub 2. So as long as x sub 1 is less than x sub 2, then the y value at x sub 1 is less than the y value at x sub 2. That is, the function's increasing. So there we go. That's the proof of part A. Part B is a similar proof, so we're not going to go through that. But there you have it. QED. Quod erat demonstratum. Now, there's not a lot to this video as far as anything else goes, so we're just going to do a simple example here and then move on. So determine where the function is increasing and decreasing. Somebody hands me a function. According to our previous theorem, as long as the derivative is positive, we know the function's increasing. As long as the derivative is negative, we know it's decreasing. Probably the best thing to do, obviously, is to take the derivative. So we're going to go ahead and take the derivative here. And this would be 8x minus 4x cubed. Now I want to know when that is positive and when that is negative, that derivative that is. The best way to do that is set it equal to 0 and make a sign chart. And here's where we start going back to previous material. Recall that a critical number for a function is where your function's derivative is 0 or the derivative just doesn't exist. Well, if you think about that, if the function's derivative becomes 0, then on either side of that point where the function's derivative became 0, the derivative might have been positive or negative. So you have these possibilities of your derivative switching signs at a critical number. Also, that can happen when your derivative doesn't exist as well. So finding critical numbers is key to this. So we're going to go ahead and search for critical numbers here. Of course, f prime is a polynomial, so it always exists. So really all we're worried about is when is f prime equal to 0? So we're back to that question. So solve f prime is equal to 0. That is, we're finding the critical numbers. So find critical numbers or chaotic neutral. All right, so let's go ahead and do this. As 0 is equal to, I'm going to go ahead and just factor out a 4x out of those two terms, and I'll get a 2 minus x squared. And you can see that this equation becomes true at x equals 0 and at x equals plus or minus the square root of 2. You can double check my mathematics, but that is true. So we now know that we have critical numbers at 0 and at plus or minus root 2. What I'll do here is just create a number line for my derivative. And this is a habit we need to get into, is creating number lines for our derivatives. So here's a number line here, and I mark it with f prime because that's going to be kind of important for me. And I'll go ahead and mark 0 on here because that's one of my critical numbers. I'm not marking 0 because it's 0. I'm marking 0 because it's a critical number. And then I'll mark a negative root 2 on there and a positive root 2 on there. And all I'm going to do is check the SIGN signs of the derivative over those intervals. Notice we have 1, 2, 3, 4 intervals that we need to check. I'll start with the one that I think most students are going to say is the easier interval. Let's start with this interval right here. In that interval, you can choose any number you want. I'm going to choose to plug in 1 because 1 is between 0 and root 2. So f prime at 1. You don't actually need to know what the value is. You just need to know, is it positive or negative? Well, f prime of 1 is easy enough to compute. It's just 8 minus 4. So that's 4. Like I said, I didn't actually need to know the number. I just needed to know it was positive. So I'll write positive. Now I will choose a number between 0 and negative root 2. Good number to choose there is negative 1. F prime at negative 1 would be a negative 8, and then plus 4, which is a negative 4, and that is negative. Notice what I'm doing here. I'm just showcasing where my derivative is positive or negative. Finally, I have these other two intervals. Now, a lot of people will say, okay, well, a number that's greater than square root of 2, and they'll try to think about square root of 2 and say like, let's see, 2 is, square root of 2 is probably 1 point something, right? Don't overthink it. Just grab a huge number greater than root 2. You can grab a number like 10, or as I do, I grab a number like 1 billion. If you grab a number like 1 billion, it makes it so stupidly large you don't actually have to do math. I have 8 billion minus 4 times a billion cubed. Obviously, the 4 times a billion cubed is much larger. So you have a small little 8 billion minus a massive number. That's going to be negative. So I know that over here, my derivative will be negative. You could plug in 2 or 5 or 10 if you want, but that requires you to possibly make an arithmetic mistake, and I don't want to do that. So that's why I'm doing it this way. If I were to go to the other edge and plug in, let's say, a negative trillion, well then, I have a negative 8 trillion, that's a hugely negative number, minus a negative trillion being cubed times 4. Well, first of all, minus is positive, and trillion cubed is massive. So I don't really care about losing 8 trillion if I have a very massive number that is positive. Or you could just plug in negative 10. Now, in this example, I think plugging in numbers like negative 10 and 5 and negative 5, stuff like that, that's simple. And you could totally do that. But in the long run, it's probably better to just plug in huge, stupidly large numbers. So anyhow, determine where the function's increasing, decreasing. Now, what I have a habit of doing is noting on here that since the derivative is positive in this interval, we know we're increasing there. Also over here, it's increasing. And it's negative on the other 2 intervals, so we know our function is decreasing here, and it's decreasing there. The patterns that I'm setting up as far as drawing out the number line, putting the plus or minuses on them, and writing increasing or decreasing, those will pay you back in the long run. Trust me, I know it seems like I'm taking a long time with this, but what I'm doing is trying to get you the skills so that when you approach a homework or an exam or something like that, you guys will be great at this material. So I happen to know now that f is increasing on the following intervals. Negative infinity up to negative square root of 2, and then I glue to that a different interval where it's increasing from 0 to root 2. Notice I do not include endpoints. Your function will never increase at a point. It increases over an interval. So do not include endpoints on intervals of increase or intervals of decrease. Okay? So that's important to note. Also, somebody had asked me recently, why do we use the union symbol? It's because you're gluing together separate intervals. So you're gluing together this interval, right here with this interval right here. And that's what a union does. An intersection takes the overlap, and we don't want the overlap. We want to glue these 2 separate intervals together. The other piece we need to state is where f is decreasing. And that one is done simply the same way, right? It's decreasing on negative root 2 to 0, and then root 2 to infinity. There you go. So that's a pretty good, robust example so far. And this is, like I said, a gentle introduction to the graphing. And as I mentioned earlier, or right at the beginning of the video, I'll be building a how-to. Every step of the way, we're going to build this recipe, I guess you could call it. And it's not my favorite thing to do, but it is kind of important to have some type of idea of how to tackle graphing. So given a function f, if you're asked to accurately graph that function, which is going to be the case from this point forward, the 6th thing you will do is deal with the first derivative. So you compute the derivative, you find the critical numbers, and then determine the intervals of increase and decrease. And then you're going to organize the information, which is what I did with that number line, and eventually we'll get to the graphing part. But that finishes out this video. You can see there are several different steps in here that I've skipped, obviously because we haven't talked about them yet. All right, I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close, don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.